strongly recommend to read a tutorial paper which just came out in IEEE Control System Magazine, which is on PageRank, by Ishii and myself. June 2004. I will have a specific reference later on. So it just came out a few weeks ago, and it is written in a tutorial-like fashion for students and beginners. It's written it took quite a while to write it, because it's written in a fashion that we decided to hide the math for those of you who are not interested in math or not particularly interested in math. For example, I have some colleagues in computer engineering who are not very deep in math, so the math is somewhat put into boxes. And also, we have some simulations for medium-sized problems. Okay, so PageRank computation in Google, randomization and ergodicity. So just a couple of words in order to connect this talk with what we talked yesterday. So randomization over networks. So we have a general methodology for handling randomization over networks, and in particular we are studying 3 different applications. So the first application that we studied yesterday is opinion dynamics in social networks. Second one was clock synchronization of sensor and wireless other networks, wireless networks and so on. And today we are going to discuss PageRank computation in Google. There is a 4th application that I'm working on, but we're still far from getting results, and that's related to smart grid. So what is common between these 3 different approaches? In particular, we are interested in developing distributed algorithms of randomized fashion, and time averaging is playing a key role in all these applications. So the 2 ingredients, distributed randomized algorithms and time averaging, are the same. However, the technicalities are very different and are very specific to each problem. So, PageRank problem, I assume that most of you or all of you don't know what is the PageRank problem, so I will start, very easy. So a couple of nights ago, in the panel discussion here, we discussed Umberto Eco, who is a famous Italian professor. In particular, he's well known because he's the author of The Name of the Rose, a famous book, which was translated in more than 40 languages, and he sold more than 30 million copies of this book. So this book has been translated in 40 languages, including Russian, and the translation in Russian is by Elena Kuznikovich. So what I find fascinating about the book, if you wish, but also Google in particular, is that if you go into Google and you type in Umberto Eco, then immediately you find his website. So this is an interesting idea, and how you can. So I was wondering a few years ago when I started looking at this Google problem PageRank, I was wondering how web searching engines are so efficient and what is behind. And so this motivated me to study a little bit this PageRank problem. On the web, you can find so-called PageRank checkers. So this is easy to download, or actually not even easy to download it. You can just go to the web and then type in the specific website. So this is the website of Umberto Eco, www.umbertoeco.it, and then immediately you get a score, which is in the range of 0 to 10, or if you wish in the interval 0, 1, which tells you the importance of the page that you are visiting. So in the case of Umberto Eco, you get 5 out of 10, which is sort of a medium grade. And whether or not this is a good indication or not, well, at the end of the talk I will make a brief comment. Anyway, PageRank, this is the definition of Google. PageRank is Google's view of the importance of the page. So if, for example, you go to some website, for example, the White House website, then you get 10 out of 10. So it means that from the Google's viewpoint, the web page that you're visiting is very important. So PageRank is a numerical value in the interval 0, 1, which indicates the importance of the page that you're visiting. And this is actually used for facilitating the web search. PageRank is used in search engine to indicate the importance of the page, but in fact there are many different ramifications and implications of PageRank. In particular, PageRank has been used in many different areas for ranking objects in order of importance. And here I want to list some of them. Scientific journals, eigenfactor, and today I'm going to spend quite a bit of time on discussing this eigenfactor, which is a variation on PageRank for ranking journals. In economics, I learned very recently what is called economic complexity, which is a variation on PageRank for started by people from Harvard in order to use PageRank on economics. Cancer biology, protein detection, there were a couple of papers by Vidyasagar and others, and Vidyasagar was using some of the ideas in PageRank, how to make a graph strongly connected. There are also other applications, for example, ranking top sport players. And there are articles which have been written, for example, regarding ranking tennis players. The point is this one. If you want to rank the top players today, then Rafa Nadal is the number 1 according to some rules which have been decided. However, the point, and then there is Djokovic and others, but then the point is that how can you compare a top player today with someone who was a top player, say, 20 years ago? And these two people never played together. So what people have done in order to attack this problem, they basically construct the graph, just checking the amount of successes, or number of competitions between, say, two specific players. So they build up a big graph, and they build sort of a structure into that, and then they use PageRank. So according to these articles, the number 1 tennis player is Jimmy Connors. Jimmy Connors. So here it's a model, which is a very simple model, which is called the random surfer model. So we have a network which consists of servers, which are the nodes, and they are connected by directed communication links. So the web surfer moves around randomly following the hyperlink structure. So the web server arrives at a certain link, and then he or she has several options, and then he picks one at random, and then he goes on and on. So here it's a little simulation which shows that. So we have a bunch of servers, which are the nodes of this graph, and then there are direct communication links. And we start, say, from this one, and we will see that the initial condition doesn't matter. And then from this one, which is a website that we visit at some point, we have several outgoing links. In this case, we have 4 of them, and we assume that all of them are equally probable, so we pick one of them at random, which is this one, and then it means that we arrive at that web page. And then from that web page, we can follow again the hyperlink structure, so we can pick, in this case we have 3 of them, so we can pick one of them at random, this one, and then we arrive at that page. And then we can continue this way. So, a couple of comments. If a page in this random walk, if a page is important, then it means that it is visited more often. So, because in this random walk, we keep visiting the page often and often. So the time that a random surfer spends on a page is a measure of importance of the page. So, if important pages point to your web page, then it means that the page becomes very important. Suppose that at Google, they have a link to Pavel's website. So it means that if people are visiting the Google website very often, so it means that it's likely that also visit Pavel's website. And the question that we can pose, which is a very natural question, is what is the probability that the website is visited? And so we want to rank the pages in order of importance, so in terms of probabilities, in order to facilitate the web search. So here it's a very simple example, just to focus on that. So we have a graph representation with, say, 5 pages, and then we have links connecting them. So it's a directed graph with nodes and represented. Notice that the graph is not necessarily strongly connected, because from page number 4 you cannot go back. So this is an important issue. We can assume that the graph is time invariant, which is actually a very strong assumption, but over time it's okay. And then we can also assume that the graph is not. So it's constructed using crawlers and spiders, which are moving continuously around. So the graph is there, is not. So using this graph representation, we can actually build a so-called hyperlink matrix. So let me just show a little example how can we build this. It's very simple. So we have a graph, and then we can build this matrix. So we work column-wise. So column-wise, so the first column, we basically look at the server number 1. And then we look at outgoing links. And then we see that number 1 points to number 2, points to number 3. And points to number 4. So there are no self loops, and the reason is will become clear later. So it means that this entry is equal to 0, and then there is no direct connection between 1 and 5. So this entry is also equal to 0. All the other elements, 2, 3, and 4, are non-zero. The matrix is normalized column-wise, so that the sum of all the elements is equal to 1. So we get 1/3, 1/3, 1/3. Now, if you look at page number 2, you see that there is an outgoing link to page number 1. So the first entry is non-zero. All the others are equal to 0. And so it's normalized, so this is equal to 0. And then you go on and so forth, and then you build up this matrix. So this is a column stochastic matrix. Actually, more precisely, this is a column substochastic matrix. Because if you look at the last column, all the entries are equal to 0. Because there is no outgoing link from page number 5. So this is a column substochastic matrix. Column stochastic matrix means that all the entries are their sum equal to 1. In this case, the sum is more than 1. It's actually equal to 0. And this is actually creating problems, which I'm going to explain in a minute. So this is what we call the issue of black holes. So the issue of black holes is the fact that the web surfer gets stuck when visiting page number 5 in this case. For example, a PDF file. If you have a PDF file with no hyperlinks, in that case you get stuck. And then at this point you can immediately realize that the problem is not well posed. The problem of computing the probability. Because suppose that these 5 servers are reservoirs with water. And so the water is circulated around. So the water is moving around, and moving around, but the water eventually will go into 5. And so all these reservoirs will be empty, and this reservoir will be full. Which basically means that the probability here, corresponding to the server number 5, is equal to 1, and all the other probabilities are equal to 0. So the problem is not well posed. So in this case, we have to work on some web modeling problem, and this is what is natural to all of us when we are in this situation. Then what we're going to do, we get stuck, we get into PDF file, say, okay, what we do? We want to continue the search, so basically we press the back button of the browser and then we go back. So this actually helps us to form a matrix which is stochastic instead of substochastic. So from this situation that we get stuck here in this black hole, we basically put an hyperlink, and then from this hyperlink, for example, we go back to page number 3. There are other ways to resolve the problem. For example, you can think about, from page number 5, you can go back to page number 4, or maybe you can put, very weak links to all the other pages. This is actually used, this trick, in eigenvalue. So anyway, whatever you do, if you fix this problem, it means that in this case, if you do this trick, this back button trick, then you get an entry equal to 1 here. So the problem is well defined. The matrix is a stochastic, column stochastic matrix. And so we don't have any more these black hole issues. Okay. So far, so good. So how you model this black hole is a different issue. So anyway, the important thing is that A is now a non-negative matrix. Non-negative in the sense that all the entries are non-negative. And it's a stochastic matrix in the sense of column stochastic. Okay, we can represent immediately this random walk, this random surfer, using a Markov chain. So using a Markov chain, we simply represent x, ok plus 1 equal to A, which is this hyperlink matrix that we now know how to build, x, ok. What is x? X is a vector with n components, where n is the number of websites. Each element of xi is in the interval 0, 1, and xi is a probability vector. So x is a probability vector, so that the sum of all xi is equal to 1. Okay. So there are probabilities, and they simply represent at time k the probability that what is the importance, or what is the probability that page I is visited at time k. Very natural viewpoint. And so you can just, you have this hyperlink structure, you build up the matrix A, and then you build this Markov chain. And then, you know, the question is also a question that Giuseppe was posed in a completely different setting, is the question of computing a stationary point. And the stationary point, the question is that, does the Markov chain converge to a stationary value? So when k becomes sufficiently large, does x of k converge to some stationary value, which is x star, for k going to infinity, or not? Do we have a stationary value, or do we have oscillations? Well, it's very simple to build up examples, saying that in general, the Markov chain does not converge to a stationary value. You can think about many examples, and the reason is because A is a non-negative stochastic matrix, so they may have oscillations. So we introduce a different model, and this different model is called the teleportation model. So this teleportation is also very intuitive, and the teleportation model basically means that, you know, we are visiting this website with this random surfer model, and then after a while we get tired of this random surfer model, and so it means that we basically jump to another page which is far away, either geographically, and then we basically continue from there. So again, showing a little simulation. We are here, so we have this random surfer model. At that point we get bored, we are looking for something, we don't find it. So what we do sort of a quantum jump. So we go far away. And this far away means that could be, again, let me repeat, could be geographically far away. So from Moscow you may want to jump to Torino, or maybe you are looking for, say, something related to control systems, and say, you know, I'm finding something related to biology, so I'm not looking in the right place. And so you get bored, you jump far away. And then, you know, from this jump away, in this teleportation, then you basically continue with this random surfer. So you continue random surfer, okay. And then from there, you get tired again, and then you make another jump, and so on. One point is that the random surfer model is, of course, you know, very stupid model, but also this teleportation model, in a sense, it's a stupid model. In the following sense, I mean, where you are jumping, if you don't know anything a priori, you are saying, well, I want to jump to any probability, any page with the same probability. So the probability that I jump there is 1 over n, where n is the number of web servers. Okay, so this model can be represented as a convex combination of two matrices. So the convex combination of two matrices, one is the hyperlink matrix that we discussed. A second matrix is a matrix S, which is a rank 1 matrix of all the entries equal to 1, divided by n. So all the entries of this matrix S over n is equal to 1 over n. And this means that it's representing the probability, which is 1 over n, that you jump to another page. So S is 1, 1 transpose using this vector notation. So 1 is a vector of all ones. So it's a convex combination between A and S. So the convex combination matrix is called M, and it's a convex combination between A and S over n. The convex combination parameter is in the open interval 0, 1. It's crucial that it's in the open interval 0, 1. We will see later why. And then is the number of pages. And you can see that if you take little m parameter, say close to 0, then this goes away. And this is close to 1. So the matrix M is very close to the matrix A. So this is the random surfer model. So the other extreme case is when m is very large, it's close to 1. So in this case, this goes away, and then this is very close to S over n. it means that you are always teleporting, so you're always jumping. And then you have all the extreme cases in between. And then you have all the intermediate cases in between. The value m is equal to 0.15 is what is used at Google. For example, Boris wrote papers related on how to accelerate convergence and how to select m in order to accelerate convergence. I'm going to give a little explanation in a minute of why this value is used. So the matrix M has some interesting properties. So M is a convex combination of two non-negative stochastic matrices, and M is in the open interval 0, 1. So it turns out that M is a strictly positive stochastic matrix. So all the entries of M are strictly positive. And that's an important point, because then we can involve theorems. And in particular, now we have a stationary point. So we have a Markov chain, which is x of k plus 1 equal to m x of k. And m is, let me repeat, is a strictly positive stochastic matrix. So assuming that the initial conditions are suitably normalized, so it's a probability vector, convergence is guaranteed by Perron theorem. I'm going to say in a minute a couple of points about Perron theorem. So we have a stationary point. So for k sufficiently large, x of k converges to x star, which means that x star is equal to m x star. Or if you wish, you can write this like 1 minus m a plus m over n s x star. And then let me repeat, is in the open interval 0. So the corresponding graph is now strongly connected. So if you are not interested in websites and so on, the trick that Villasagara used in some of his papers related to cancer biology, the graph related to this cancer biology problem was not strongly connected. So Villasagara was using this trick in order to make the graph. But he was not really doing ranking. Well, this is a picture of Green and Page, the founders of Google, when they were students at Stanford, and then they didn't finish PhD because they had something else to do. So there was a first paper that they published, which is called, the title is Bring Your Order to the Web. And then there was another paper with Motwani, who unfortunately passed away a couple of years ago. He was at UCLA, Stanford. And Vinograd is also in some California school. I forgot to read this. Yes, they are both at Stanford. So another paper with their advisors. Clearly, Motwani and Vinograd, they knew a lot about randomized algorithms and Markov chains, and so this is what Green and Page typically learned from them. So the ranking is now provided by x star, by the stationary value. So PageRank x star of the hyperlinked matrix M is now defined as mx star equal to mx star, where x star is a vector with m components, and each component is in the interval 0, 1, and then is suitably normalized, so that is probably 12. So that's the definition of PageRank. There are two different interpretations. One interpretation is the Markov chain interpretation, which I gave you. X star is a stationary value of a Markov chain, so which is a steady state probability that pages are visible. There is a second interpretation, which is a linear system interpretation. So x star is a non-negative unit eigenvector corresponding to the eigenvalue 1 of the matrix M. And the two interpretations are equivalent. It's just a matter of how to present it. I gave a talk to undergraduate students in Milano. There was a Politecnico di Milano, about 1 year ago, invited by our colleague Sergio Bittanti, and I presented the other way around. So I presented this like an eigenvalue-eigenvector problem, and then I gave later on an interpretation in terms of Markov chain. Well, you know, for undergraduate students it was perhaps a little harder, so it's more intuitive to give them the interpretation in terms of Markov chains, and then later on just to observe that, by the way, this is an eigenvector problem. Well, just a couple of comments on Perron theorem. So this is Perron theorem because we are dealing with matrices which are positive. there is another theorem which is Perron-Frobenius, which deals with matrices which are non-negative. So stochastic matrices are Perron theorem, just a couple of observations. The eigenvalue 1 of m is a simple eigenvalue, and any other eigenvalue, possibly complex, is strictly smaller than 1 in absolute value. There exists an eigenvector x star of m with eigenvalue 1, such that all the components of x star are positive. And m is a irreducible matrix, and the corresponding graph is strongly connected. So from this point of view, I mean, if you think about the graph and not the matrix, you see that from I and j, which are two servers, then there is a sequence of edges which connect I and j. And x star is a stationary probability vector, x star exists in it is unique. So the problem is well defined. Of course, the problem is how to compute it, but that's a different story, which is the PageRank computation. Well, I mean, we can simply compute it using the so-called power method, which is just an iteration of this code. It's called power iteration, power method. So we basically just run this iteration, x of k plus 1 is equal to m, x of k, and if the initial condition is suitably normalized, convergence is guaranteed because m is a strictly positive matrix, and we know that there is a stationary value by Perron theorem. Now, the issue what they claim at Google is that the PageRank computation requires between 50 and 100 iterations. So that's pretty fast. I mean, this convergence is quite quickly. On the other hand, unfortunately, due to the size of the problem, this computation takes 1 week, and it is performed centrally at Google once a month. In fact, a personal experience that I had, when I made substantial changes in my website, and then I was looking at R.Tempo in Google, it disappeared. It disappeared from the top of the search, and then after a few weeks, it came back. So it seems that somewhat it needed some adjustments, and then PageRank computation was computed again. It took a few weeks before they were doing the computation, and then once the computation was done again, my name appeared again at the top of the list. Okay, before going on, let me just show another simple example with 4 websites and show that PageRank actually makes sense. So we have a website for, and then we simply build in the matrix A, which is this one. We know how to build it. We take the value, the parameter m equal to 0.15, and we go to MATLAB and then compute m. Computing m directly is actually a very stupid idea, because A is a sparse matrix and m is not a sparse matrix. But in fact, the explicit computation of m is not necessary. We will see that later. Okay, and then we simply compute the eigenvector corresponding to the largest eigenvalue, and this is what we get. Okay, let's look at this. So this is normalized so that the sum of all these elements is equal to 1, and this should provide a rank. So according to this one, the smallest one is 0.12, which is page number 1. It makes a lot of sense, because the only way to visit page number 1 is using this hyperlink. So this page is unlikely to be visited. So that's why it's at the bottom of the search. And at the top of the search, there is 0.333, which is page number 2. Again, it makes a lot of sense, because there are many links which allow you to visit 2. From 1 you can go to 2, from 4 you can go to 2, and from 3 you can go to 2. So page number 2 is very often visited. And then there are the other 2 intermediate values, which are similar but not exactly the same. It means that it's not only the number of incoming links, but also the number of links. But the problem is that the size of m is more than 8 billion, and it is increasing, and so this is a very hard problem. Why m equal to 0.15? Well, the asymptotic rate of convergence of the power method is exponential, and then it depends on the ratio of the second largest eigenvalue divided by the first largest eigenvalue. Well, at this point we know that the first largest eigenvalue is equal to 1, And the second largest eigenvalue, the absolute value, can be easily shown at a few computations, it's not hard, to show that this is bounded by 1 minus little m. And so little m is 0.15, so this rate of convergence is bounded by 0.85. And so if you run 50 iterations, then you see that the accuracy is in the order of 10 to the minus 4. 100 iterations is the order of 10 to the minus 8. Larger m implies faster convergence, but then it becomes very, very delicate. In fact, from the linear system viewpoint, it means that you have a discrete time system, and you have one eigenvalue, which is equal to 1, and then the second largest eigenvalue is bounded in a circle of radius 0.85. It is somewhere, and all the eigenvalues are over there, but they are bounded in this circle. So in principle, of course, you can accelerate the method. I mean, you can, put eigenvalues larger and larger, but then you can get, very close to numerical instability. If you have too many eigenvalues which are very close to the boundary of the unit circle. So it's still sure stable, but it's actually delicate. There are many other issues, and people in the numerical analysis literature, they studied this from the point of view of sensitivity. So you can actually compute the sensitivity, in the sense of the derivative with respect to the parameter, and then you can make some conclusions. Well, here is a picture of the Columbia River, the Dallas, Oregon. Many IT companies, Google included, but also many others are buying land there. And the reason why they are putting lots of circles there, because land is cheap. It's a very remote area, so it's cheap. So electricity is also cheap, and in addition there is this river, the Columbia River, and so you can use the water as a cooling device for all these computers there. So, well, here we take a different viewpoint, and we take the distributed viewpoint. So more and more computing power is needed, and here is what we discussed yesterday. So instead of a fully centralized model, we want to work with a distributed model. We want to work with a distributed model which has several advantages. And so one is because it's hard to compute, to know global information about the network. And so we want to work with a distributed model. One, and we are using, as I mentioned at the beginning of the talk, we are using randomization. One key difference between what we discussed yesterday and what we are discussing now is the kind of randomization that we are taking. Here, randomization, it means that at time period, you pick one solver at random, or maybe in this case two, doesn't matter. So we are working with vertex randomization. Yesterday, for example, in social networks, we are working with link randomization, because there are two people, say Leven and myself, who are talking, and so you pick two people at the same time, or more than two, but at least two people. So it means that it's like an edge. So link randomization versus vertex randomization. So that's different. So randomized decentralized algorithm. So the main idea is to develop a Las Vegas randomized algorithm, which is has the same features that we discussed yesterday. The technique is completely different because it's based on picking vertices instead of picking edges. And it's randomized and it's decentralized and so on. And the protocol that we are also looking is very similar to the protocol that we had yesterday, which is called the glossy protocol. So you basically look at information which is local, so you exchange information with the pages that are close to you. So again, this for example, this example with 4 pages, and we will see that it's randomized. So at time k, we randomly select a page, which is in this case is page number 4, in this picture, with a uniform probability. It's important that the probabilities are IID. I mean, they can be also non-uniform. It doesn't really matter, but they should be IID. So this gossip communication protocol proceeds in 2 steps. First step, with say uniform probability, you pick one page at random, page number 4. And then the second one is that this page number 4 broadcasts information. So at time k, page number 4 knows what is page rank value of this page, and this page rank value is actually transmitted to the neighboring pages. So send the page rank value of page I to the outgoing pages that are linked to page I. Okay. This protocol is a gossip-like protocol because we are not using information between 2 and 3. So as you can see, we are only using outgoing links. So outgoing links is the link connecting 4 to 1, 4 to 2, and 4 to 3. We are not using, for example, the link between 1 and 2, because this is not gossip, so it's not close to 4, it's far away. Okay? At the beginning of this adventure, we had another protocol which was actually less realistic than this one. It was using information about the outgoing pages and information about the incoming pages. This information about the incoming pages is not really realistic, because in order to know what are the incoming pages in my website, I need to perform a global search into the web. I know what are the outgoing pages, I don't really know what are the incoming pages, but that has been fixed. But the first papers that we published on this had this more complicated protocol. So again, we pick one page at random and then we broadcast it. So here we go back to the issue that we discussed yesterday about global clock. And so we have to define a clock. What is the clock? Well, the clock is a stochastic process, theta OK. So it's a random process which evolves over time, and it takes values which are 1 to n. So 1 to n are the n pages. So it means that at time k, if at time k we have theta k equal to I, it means that with probability 1 over n, then it means that page I initiates the page rank update. So broadcast it to the right. So theta k is assumed to be IID with uniform probability, not necessarily uniform. So theta k plays the role of the clock, which is a global clock known to all the pages. Yesterday, in particular, when I was discussing the problem of clock synchronization, I said that in the case of clock synchronization, the issue is that you don't have a global clock. And so you want to work with a local clock. Here, unfortunately, for two reasons, we need to assume that we have a global clock. So this theta k stochastic process is known to all the pages. And there are two reasons why we do that. The first reason is sort of technological. You can assume that all the pages that are connected have the same clock. Perhaps it's a reasonable assumption. The second assumption is that we don't know how to remove the assumption of global clock yet. So it takes more work. Okay, so we have theta k, this stochastic process with this global clock, and then we basically work a randomized update scheme. The randomized update scheme is the following: x of k plus 1 is equal to a of theta k x of k. Okay, where a of theta k are the so-called decentralized link matrices, which I'm going to explain in a minute. Okay, this is yesterday I mentioned briefly Markovian jump systems. Let me emphasize again that this is a so-called Markovian jump system, which perhaps this property can be used to prove some convergence properties. Anyway, so this is what we have. So what are the decentralized link matrices? We have to specify. So this is the matrix A corresponding to our 4x4 example. And then we work with this protocol that at time k, we pick page number 4 at random. Okay? So from page number 4, we have all the outgoing links. What are all the outgoing links? Well, all the outgoing links correspond to column number 4. Okay? Notice that this protocol is a gossip type. So we are not using information between, say, page number 1 and page number 2. So the result is that all the other non-diagonal entries are set to 0. So because we want to use only information based on this outgoing link from page number 4. So all the other elements are set to 0. And then in order to make things work, we need to set the remaining diagonal elements equal to 1, so that this matrix is well defined. This is a stochastic matrix, it's a column stochastic matrix. We can do the same, so if at time k we pick with probability 1 out of 4 page number 3, we do the same. So in this case the outgoing link corresponds to this third column. due to the gossip protocol, all the other elements are set to 0, except for the diagonal elements, which are set to 1, so this is also well defined. And then you can define day 1 and day 2 in the following way. Well, we have to talk a little bit about what are the properties of this. Well, now we have this A of theta k matrix, and then we want to compute the expectation of this matrix. So what is the underlying random variable? Well, the underlying random variable is theta k, so when I write A of the expectation of A of theta k, I mean the expectation with respect to the random process theta k. And I call this the A average. So taking uniform distribution in this stochastic process, then immediately I have that A average is 1 over n of the sum of these matrices A average, because they are independent. And here there's a little property which tells us the properties of this matrix A average. Well, this matrix A average can be actually computed in closed form in terms of number of pages, which is n, A, which is the matrix, the hyperlink matrix A, and in terms of the identity matrix. So now, if we have a website which has lots of pages, then n is very large, that means that this goes to 0, and this goes to 0, so A average is basically the identity matrix. Okay, so that's the extreme case. Well, what is more important, perhaps, is the fact that A and A average have the same eigenvector corresponding to the eigenvalue 1. So it means that A and A average, they share the same page rank, so I can actually work with A average instead of A. However, there is more to say. We have to remark that we need to work with matrices which are strictly positive. So we have to remove the zeros. So remember that we have to work with the matrix M. So we have to work with an iteration which is x of t plus 1 equal to m of theta k x of k. What are m of theta k? M of theta k are the modified decentralized link matrices, which are given by a convex combination which is similar but not exactly equal to the one we had before. So mi is equal to a convex combination, where now we have a convex combination parameter r between the AI matrices, which we just defined, and the matrix S over n. R is a convex combination parameter which is in the interval 0, 1. However, it's not exactly equal to n. So we need, this is a design parameter, and in particular we take R given by this formula, where m is 0.15, n is the number of web pages. So if the number of web pages is very large, then here in the denominator we get something very large, and R becomes very close to 0. Again, we have to study some properties of the average matrix, which means that we have m of theta k, and then we can study the expectation with respect to the stochastic process theta k of m of theta k, and we call this m average. R is defined as follows, and there are a couple of properties that we can prove about this matrix M average. Well, the first one is that R is well defined, so it's in the open interval 0, 1, so the convex combination that we had before is actually well defined, so it's a well defined convex combination. R is actually smaller than 0.15. As I said, if n is very large, then it can be very close to 0. However, what is probably more important is the third property. The eigenvalue 1 for M average is the unique eigenvalue of maximum modulus, and PageRank is the corresponding eigenvalue. So, which means that PageRank, the PageRank for M of theta k and the PageRank for M are the same. So I can actually work with this stochastic process. However, it's crucial, again, to use time average. So without time average, I mean, things do not converge. One issue that I want to remark again, if we take time average, unfortunately, we slow down convergence, because we have 1 over k rate of convergence. And this comes out quite clearly if you look at our proofs, that basically you see that you're stuck with this, but then you get convergence. So that's the price that you pay. You slow down convergence, however the computations are performed in a distributed fashion. So, let me repeat. Here you get slower convergence compared to the power method. It's not exponential, convergence is 1 over k. However, these matrices are very sparse. Most of the entries, except for the diagonal ones, are non-zero. You can even think about other protocols where you are not using all the outgoing links. You are using only some of the outgoing links. The metric becomes even sparse. Convergence becomes slower, but then all the entries in this matrix are basically zero. So then you can write these equations instead of a matrix form, you can write this equation in a component-wise form, as I was doing yesterday for the other problems. So most of the time, all the components of the PageRank value is not updated. So convergence becomes extremely slow, but computation is very cheap. So these are pros and cons. Well, then we have the theorem which tells us the convergence properties. So time average y of k of the modified randomized update scheme converges to PageRank in mean square error. So again, PageRank is hard to compute because you have to solve an eigenvector problem for a matrix M which is 8 billion. In this case, you build in principle a matrix, but you can write component-wise. You take time average, you compute y of k, and then asymptotically, this is what you get. The only assumption that you need is basically you have theta of k. There are two assumptions. One is a priori assumption about this a priori probability, and the second assumption is that theta of k that you build up should be an IND process, which is, I think, a very result.
What is the rate of convergence of such convergence?
1 over k.
1 over k?
Very slow.
I guess 1 over k is the power of 2.
Yeah.
Not first.
Yeah.
Power 2. K?
Yeah.
I see.
In fact, you know, there are issues on how you can improve the rate of convergence. So if instead of taking averaging, entire time averaging from 0 to k, when k is very large, why you have to deal with the k's which are, you know, down in the past? How can we improve that? I don't know. It's
I mean in this formula.
Yes.
In square.
Yes. This is mean
you
square.
have in the right hand side instead of 0 estimation. For example, O large of 1 of k or 1 of k in the power of 2. What is the power of?
The way that the proof works, the proof is based on the theory of ergodic matrices. So we have to form all the possible multiplications between these matrices A1, A2, A3, and so on. And then we basically compute, it's a brute force approach. So we compute what is called the coefficient of ergodicity. And then we have to bound this coefficient of ergodicity, and then there are various factors in this coefficient of ergodicity. And what happens is that when k is very large, then we show that this quantity goes to 0.
I understand, but we have an estimation of the spectral gap of the matrix is 0.15, and so we can estimate the rate of convergence.
This is not done yet, so it's an open.
I see.
So that will be interesting to address that.
Okay.
As I mentioned at the beginning of this lecture, we didn't know much about ergodic matrices and so on. Then we basically the proof was sort of very detailed, very involved, and lots of computations on this coefficient of ergodicity and so on. Some of the results around in the theory, by example, the book by Seneta, and there are many other books, actually can simplify this. So, in fact, a couple of comments. Other people, Han Fu Chen and other people from Chinese Academy of Sciences, actually they proved almost sure convergence properties of the algorithm. So they prove other properties, stronger properties of our algorithm. And in fact, almost sure convergence, I think it's now clear that you can easily prove it. And how you can prove it? Well, I mean, you can observe that this is a Markov jump system. And then, for example, if you look at the book by Costa and Fragoso, Markov jump system, you see immediately that mean square error convergence implies almost sure convergence. So you basically get that result for free. And so, but again, this is something that we didn't know. So there is this very nice paper which came out in the Transactions by Han-Fu Chen and others. So it was actually flattered that these people, thought that it was interesting enough in order to try to improve it. So I have some comments that I want to make. And some comment that I want to make is, first of all, the time average can be computed recursively as a function of y of k minus 1, of course. The second point that I also, in terms of open problems, here we just use a brute force approach in terms of time averaging. Can we do some sort of forgetting factor? So if we put some forgetting factor, then perhaps we can improve speed of convergence. I don't know, this is not done yet, so it's also, so this is something that we just discussed. Well, one important comment that I made before is that in this 4x4 example, I can add the matrix A, I can actually compute M, but if I compute N directly, I do something very stupid, because here the approach is to try to work with matrices which are fully sparse. And so if I compute N directly, I do something which is very stupid. However, this is not necessary. This is not necessary, because x of k plus 1 of k can be written as follows: 1 minus r k x of k plus r over n 1, where 1 is a vector of all ones. So from this point of view, you don't need to compute explicitly m. You can work directly with the matrix A, which is sparse, and then you have this input. So which is another interpretation which I think is interesting from the educational viewpoint in terms of linear systems. So this is a linear autonomous system. This is another linear system, but now we are forcing input. So this is another interpretation that perhaps it's interesting. Of course, you can do the same not only for the matrix A and for the matrix M, but you can do this for the matrices M sub k, sub theta k, and I of theta k. So you can work with this. We have some little results on stopping criteria to compute approximately PageRank. So when you can stop, at Google, as I mentioned, they stop after 50 iterations or 100 iterations. So what you can achieve when you stop, after 100 iterations? What is the approximation that you get? So you get, say, an approximated value of PageRank, say, call it x tilde, and then you have a true-value stop. Can you bound this quantity somehow? Or more precisely, you have x of k minus x tilde. You want to bound this. You want to find the smallest value of k such that this quantity is bounded by it. There are other extensions. Clearly, in a web, you have lots of pages. So to work with one extraction of a random page at a time doesn't make much sense. You want to extract more than one page at a time. So this forces us to work with Bernoulli processes and so on. So there are some technicalities, but it's more or less the same ideas. So simultaneously update on multiple web pages. This is also a question that some of you were posing this morning or yesterday related to the problems that we discussed yesterday. Why one edge? Well, in the social network problem, if you have, say, two or individuals who are talking at time k, then you pick one edge. If you have three individuals, then you can pick two edges or more than that. So here is the same idea. So in other words, in order to accelerate convergence, you pick more than one page at a time. We also published a little paper on fragile links. So as I said here, the web is assumed to be time invariant, which is a very strong assumption. But what can you say if some of the links are fragile in the sense they have a probability of failure? So this is something that we talk. One issue that is open, as far as I know, no, it's definitely open. All web pages need to know the global clock. So theta of k is known to all the web pages. How to work with a local clock? We tried, perhaps not hard enough, so maybe other people can do that. So to work with a local clock instead of a global clock, which is a more general problem that I think is very interesting, to work on stochastic approximation methods, not on time averaging, but when you have a parameter which is decreasing. So then you can get maybe exponential convergence. However, this parameter should be known to all the pages, and perhaps in a distributed computation fashion, perhaps that's not really a reasonable assumption. I want to make now some discussions on how these ideas have been used, I think, very effectively in different contexts and different applications. So one application is ranking control journals. In general, is ranking journals of important controls. So here is the website of ISI, Institute of Scientific Information, Web of Knowledge. And if you go to this website, then there are lots of journals. In particular, here I'm thinking about having in my mind control journals, but you can think about, say, optimization journals or whatever. The discussion is absolutely general. But then I will show some results related to control journals. And then, a classical criterion for ranking journals is the so-called impact factor. What is the impact factor? Well, first of all, the impact factor for the year 2012 is the most recent available now. Why is that? Because the impact factor at the end of 2012, basically the situation is frozen, and then it takes several months, about 6 months, to do all these computations that are required to compute the impact factor, and generally around the month of June, so the impact factor is released. So in June 2013, if I'm not mistaken, June 19th, so they released the impact factor for the year 2012. So the impact factor for the year 2013 should be known any day. So in fact, yesterday and the day before, I was sending out emails to Elsevier and said, where is the impact factor? I am very curious, and it's not known yet, so it takes a few more days, but it should be released very soon. Anyway, this is the most recent one. The impact factor for the year 2012 is the number of citations in 2012 of articles which are published in the two previous years, 2010-2011. Divided by the number of articles published in 2010-2011. So there is a census period, which is 1 year, 2012, and then there is a window period, an observation period of 2 years, the previous years. So here it's an important remark. The impact factor is a flat criterion. It does not take into account where the citations come from. So if Automatica is receiving citations from Nature, or from, say, from IEEE transactions automatic control, they are counted the same way. So it does not take into account where the citations come from. And this goes back to the discussion that we had at the beginning. If Google website, there is a link to Power website, then Power website becomes important. And here, all the citations are counted the same way. So this is what we call a flat criterion. There is another criterion, which is officially within ISI, which is called eigenfactor score. By the way, there is also another criterion here, the impact factor, which is the so-called 5-year impact factor. So there is a window period of 5 years. However, it's the same idea, but it's used less often than the 2-year impact factor, which is the classical. So eigenfactor, Bernstrom, who is a professor of biology in Seattle, he started this idea and he had a company, and the idea was to rank journals using ideas from PageRank. And so he has been very successful, I don't know from the financial business viewpoint, but he has been very successful because this indicator is now, since a few years, is an official indicator within ISI. So ranking journals using ideas from PageRank computation is good. So this is not a flat criterion. In eigenfactor, journals are considered influential if they are cited often by other influential journals. So if a very important journal, Nature, cites Automatica somewhat, then Automatica eventually will become very important. What is the probability that the journal is cited? Same question as PageRank. In fact, there are two Bernstrom. I'm always confused because one is C2 Bernstrom, the other is TC Bernstrom, one is the father, one is the son. But then there is another person, West, who was a PhD student of one of the two Bernstrom, or maybe both. And he wrote a thesis, which is actually quite interesting. And there is a nice sentence in the thesis, which I want to read. Imagine that a researcher is to spend all eternity in the library, randomly following citations within scientific periodicals. So the researcher begins by picking a random journal in the library, And then from this volume, a random citation is selected. The researcher then walks over to the journal referenced by this citation. The probability of doing so corresponds to the fraction of citations linking the reference journal to the referring one, conditioned on the fact that the researcher starts from the referring journal. From this new volume, the researcher now selects another random citation and proceeds to that journal. This process is then repeated at the field. This is what I call the random reader model. And it's, it's the same idea that you move around and then you do this. So you have a directed graph, which are now journals, and then citations. Okay, so the first thing you have to build up is so-called cross-citation matrix. This cross-citation matrix has entries Aij, which are the number of citations in 2012 from Journal J to articles published in Journal I in the previous 5 years. So in this case, we have a window period of 5 years. But this is something that we can also do with the infrastructure. What is important, however, is that this matrix is built so that the entries into the diagonal are set to 0. So self-citations are removed. And this actually prevents, as you know, there are discussions in the scientific community about journals having editors who are encouraging authors, encouraging even software, even more than that. They are sort of pushing authors to add citations to the journals in order to get it published. And this is something that IEEE is taking actions on. Anyway, and then we have to normalize it in order to obtain the constant stochastic matrix. Okay, so we have a constant stochastic matrix, and self-citations are omitted, and then just a non-triviality assumption here. Okay, and then in principle we have the same issue as before, black holes. So black holes in this case are journals which are not citing any other journal, which is perhaps unlikely to happen, but there is a way to fix this. So we have A is actually a substochastic matrix. So they have to build a so-called article vector, which is a probability vector. And the article vector has component B, has component BI, which is the number of articles published by Journal I in 2007-2011, divided by the number of articles published by all journals. So BI is the fraction of all published articles coming from Journal I during the window period. The article vector by construction is a stochastic vector, and by the way, the total number of journals in the order of 8,000. So from the computation viewpoint, this is not a serious problem. You can compute eigenvectors of a matrix easily, of a matrix 8,000 by 8,000. So in this case, they play with a trick which is different than the back button. In the back button case, we were basically going back from page number 5 to the page that was previously visible. In this case, they actually add, instead of this matrix 0, they had the article vector, which means that they had some very weak links to all the pages. So, for example, here we have V3, which is what I defined, V4, and so on and so forth. Why, there is one point which I don't understand why they do that, why they also put a self-link here, V5, not 0. This is something that I don't understand, because in this case it would make more sense to have V5 equal to 0 and to renormalize it so that, probably doesn't change anything, but still from the conceptual viewpoint, this is actually wrong, because you are actually adding citation to yourself, so it's a self-loop. Anyway, this is what they do. And again, we can work with this matrix now. A tilde, x, OK, is a vector with, say, 8,000 journals. Each component is in the interval 0, 1, suitably normalized. So it's a probability vector. And this is called journal influence vector. And XIOK represents the importance of the journal. And question that we can pose, again, exactly as before, does the Markov chain convert to a stationary value, which represents the probability of citation? At this point, I think it should be clear that the answer is no. So they have to work again with this modified Markov chain. So instead of working with the matrix A, they have to work with another matrix M, obtaining what they call eigenvector equation. And the interesting thing is that instead of working with a vector, with a matrix here, from having all the elements equal to 1, maybe divided by n, Here, they are actually working with a matrix, which is a weighting matrix. So where in the columns are V, V, V repeated 10 times. So they basically take into account the structure. So the probability that from one page you jump to another page is different than from the probability of jumping to another one. So the place where you're jumping to is not, are not the same probability. So this is interesting because they take into account some weighting factor. So this is different than the classical 1-1 transfer. Okay. They have some information, so they can use it. So why you want to have uniform probability if you have some information? They have some information which is contained in the vector V, so they use it. So the question is, what about n equal to 0.15? I never found in their papers or thesis the value that they're using on m equal to 0.15. I'm a terrible programmer, but I know how to read code. So I actually downloaded the eigenvector from the web. I went into the code, and actually I found that they use exactly the same value, 0.15. Why they don't say that, I don't know. So from the journal viewpoint, the interesting fact is that here, if you are just moving around journals in biology, and then you're not looking for something which is interesting to you from what you're looking for, instead of being tracked in a small set of journals, then you want to jump to a different content. So you jump far away to journals, say, in control systems, and then, from there, you move on and so forth. So you have now a Markov chain M. So convergence is guaranteed by Perron theorem. M is a steeply positive matrix. So we know that we have a stationary value. Corresponding graph is strongly connected, and it's an eigenvalue. X star is called the journal influence vector. We know from Perron theorem that it exists, and it is unique. And it can be easily computed because the matrix M, once it is known, it's 8,000 by 8,000. So it's not difficult problems in mathematics. Well, this is something that we can skip. I mean,
why there is no convergence in case when m is equal to 0? The situation differs from the previous one because we have a matrix A not sparse like PageRank because we defined cross citation, and I guess in such a situation
it is true.
Condition.
You're right. You're right. In this case, it is. You're right. In that case, it can be shown that you have convergence.
This is another model. I guess.
This is another model.
Okay.
This is another model. And in fact, it's related to the question why we are taking 0.15. They never say that explicitly.
This allows us to converge faster.
Yes, you're right. On the other hand, here, fast convergence is not really critical because the number of journals in the order of 8,000.
I see.
So
yes,
it's increasing.
Yes.
I mean, it's increasing every year that there are new
see.
journals and so on, which is, by the way, I think it's a bad idea to have new journals and new journals and new journals. This is a different story. So if you go to MATLAB and then you compute the eigenvector corresponding to the largest eigenvalue of a matrix, which is 8,000 by 8,000, you can do it.
I see.
But you're right. Well, I mean, you can exploit, sparsity, but this is not very important. Okay, in fact, using the journal influence vector represents the steady state fraction of time spent reading each journal. X star provides the weights to the citation values. And then they define the so-called eigenvector, which is a normalization link. So the eigenvector EF of the journal J is the percentage of the total weighted citation that the journal J receives. So the definition of eigenvector J, they multiply by 100, and then they take AX star, the Jth component, and then they suitably normalize. I wish I have the values of X star, but I couldn't get them so far. I actually pressed severe hard, and they didn't release to me, for reasons that are not known to me. So what is known is the eigenvector, and what is known is another measure, which is the article influence score. Now they denormalize it, so they basically divide by 100 now, and so they get rid of this 100, and then they normalize it with VJ. But this is not very often used. So what is very often used is this. So here is a chart showing comparisons between, say, 10 top control journals according to the impact factor and according to the impact factor. As I said, this is the 2012 impact factor and 2012 agent factor. The most recent available in a week or so, or even less, it could be even today. So perhaps the 2014 will be. So the two top journals from this point of view are Automatica, which is now since a few years is the top one in terms of agent factor, and IEEE transaction supply. You can see that these values are very close. So from this point of view, perhaps you can conclude that these are the two top journals. Then number 3 is IEEE Control System Magazine, and then they go down, 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 and then Science Journal is here. I'm going to make comments about that. IEEE Control System Magazine is very high. Now, if you look at the other ranking, according to the eigenfactor, you can see that TAC is number 1. It was number 2 last year. Automatica is number 2. It was number 1 last year, so they are basically swapped. Cyan is number 3, and then Control System Magazine is down the bottom. One observation before making specific comments is the following. You see that here, these two values are very close. The third one, Cyan, is actually, there is a big gap between the second one and the third one. You know, similarly, the first two are similar values, the third one, there is a big gap. Now, my interpretation, so this is a fact. Now, what is my interpretation? Why IEEE Control System Magazine is ranked very high here and is ranked very low here? Well, the interpretation is the following. IEEE Control System Magazine receives lots of citations, so it ranks very high according to the impact factor, which is just a flat criterion counting the number of citations. However, if you look at the number of quality citations, the number of important citations, IEEE Control System Magazine is not receiving a large number of quality citations. That's one is to the bottom here. Which actually makes sense because it's a magazine, so it's a different purpose, either to write say, tutorial papers or to have advertisements or reports about conferences or activities about the society or so on. So it's a different purpose. Cyan, which I consider I never published in Cyan for reasons that are not even clear to me, but I never published in Cyan, I never submitted paper. Is not receiving a large number of citations. Nevertheless, they are good quality citations. Perhaps it's because it's a sort of a maybe little narrow journal, so it's not receiving lots of citations, but they are good quality citations. So according to this one, this ranks very high. And then there are others. I mean, for example, Control System Technology, which is an applied journal, is more or less ranked number 4 in 2, and many other comments that can be made. So anyway, this is a fact, and it's interesting to compare both. There is a report by Gianluca Setti, who was Vice President of IEEE. Gianluca Setti is a colleague of mine from the University of Ferrara. He is a person working on circuits. And he was Vice President of IEEE for publications. And he wrote a report, and he was making lots of comparisons between different criteria for ranking journals and so on and so forth. At the end, the conclusion of the report was perhaps very simple. The report is available on the web, it's public domain. I mean, look at more than one criteria. That was the essence of his message, which is, perhaps very obvious, but it makes a lot of sense. And from that point of view, I mean, if you look at more than one criterion, you get different, then you get too many, then you get confused. But at least, to look at 2. I think I'm getting close to the end because I want to also talk about other things. There are some connections between consensus and PageRank. I don't want to go into details here, but I want to show a chart which somewhat summarizes differences and similarities between PageRank and consensus. So, of course, the objective is very different. In the case of PageRank, the page values converge to a constant, and this is what is the objective. The objective is to compute X star. Here, I mean, the objective is to design algorithms so that all agent values, say the position, the velocity, whatever, becomes equal. So they are completely two different objectives. Now, from the point of view of consensus, it's a reasonable assumption to assume that you have a strong connectivity in the agent graph, because you have, say, robots which are moving around, or UAVs, and it's very reasonable to assume that UAVs communicate and you have complete connectivity with them. Here the web is clearly not strongly connected. I mean, there are lots of places where you don't have connectivity, so the graph is really not strongly connected. So you have to make it connected, strongly connected, using this idea of this teleportation. From the technical viewpoint, we are seeing that AI and MI are column stochastic. On the other hand, from consensus, the problem is the dual one, so you are working with non-stochastic analysis. Self-loops, well, I mean, here we are not allowed to play with self-loops, because self-loops is like spamming. And in fact, this is a question that many people ask me, and I don't know the answer. How you can detect in a reasonable fashion if a web page is spammed. In my opinion, the way to attack the problem would be to deal with time-varying graphs. And then if there is a time-varying graph, and in particular there is one website which is broadcasting to many websites, so providing lots of outgoing connection in a short amount of time, then it means that you can define this website like a spamming website, then you can identify it. But in order to do that, which in my opinion makes sense, you have to deal with time-varying graphs. And so right now, I mean, the theory is limited to the fact that we are working with time-varying graphs. We have some ideas on how you can perhaps extend to time-varying graphs, but it's too early to say. Self-loops in the agent graph, this is often done, because you can actually, when you have a UAV moving around, you can actually assume that the UAV is actually transmitting information to itself about, for example, the position of the velocity. In order to get convergence result, we have a stochastic vector, initial condition. Here there is no assumption about convergence in terms of, no assumption about this one. Time averaging is not necessary. Averaging, at least the way that we played with, is so these are differences and similarities.
But the arranging in PageRank is not necessary if we have a periodic situation, and the situation is atypical.
This is another line of direction. We didn't use that. I think it could be interesting also. I don't know much about this, but I found it interesting, and so I spent a little time talking to some colleagues in Italy about they are experts in economy, and there is something that came out from two people from Harvard, Hidalgo and Hausman, what is called economic complexity. So I just have 3 slides because this is the little I know. So basically, they built up a so-called bipartite graphs, and the bipartite graphs consist of countries and products. So the countries in this example, there are 5 countries and there are 4 products. So if the graph is bipartite, so that the countries are exchanging information with the products. For example, Italy is selling shoes, and Russia is selling oil, and so on. So there are connections between countries and products. There are no connections within the countries, there are no connections within the products. Okay? So we build up, in principle, a bipartite graph. And the idea is to construct a binary cross-product matrix M, and then in principle we want to compute the PageRank value XV star related to the countries and the XU star related to the products. The PageRank value X star V is called the fitness of the countries, and this is called the quality of the products. The problem, however, is more difficult because, from the economic viewpoint, because in fact it's a tripartite graph. So because there are countries and products, but there are also capabilities. Now, the available data that people in economics have is related to countries and products. This is what is available, data available. Nevertheless, the model is different because there is something like hidden into the model, which represents the capabilities of a country to produce a certain product. And so this leads to a theory that I'm definitely not an expert on this, theory of hidden capabilities. So, to make a long story short, basically they build up a nonlinear system of this form, x of k plus 1 f x of k, where x now represents both the countries and the products, and then they iterate. In fact, there is no guarantee of convergence. So there is no guarantee of convergence. So it's an open problem for how you can suitably modify the algorithm so that you get convergence. I think it's an interesting problem in some of the papers that I was reading, but as I said, I don't know the problem at all. I just got interested because there were a call for proposals recently on this topic. And so they actually claim that the algorithm probably does not converge. Actually, I'm sure that it does not converge because there are ugly nonlinearities. But perhaps it's possible to regularize the problem so that you can get some nice results. So anyway, this is another line of direction that could be useful. This is all I know about this. I think I'm getting close to the end. I just want to spend a minute or two saying that there is another important direction. We published a paper in the transactions with Hideaki Ishii and R.Tempo, where we are dealing with aggregation ideas. So aggregation, PageRank, and complexity. Aggregation is a tool to break complexity. There are many applications where actually that could be another direction in order to deal with problems which are too large from the mathematical numerical viewpoint. And so the idea is to play with ideas which are based on web aggregation. So this is the transactions paper. So the idea, which perhaps makes sense, is that you have a web, which consists in this case of, say, 6 servers. You try to aggregate some of the servers here, for example, at Polytechnic di Torino, and then you aggregate some servers here, and then you aggregate servers here. So you do some sort of 2 times scale Markov chain. The first time scale, you actually compute the PageRank for U3, for U1, and for U2, and then you go inside the model and then you compute another Markov chain model here. These ideas of 2-time Markov chain were originally proposed a long time ago by Kokotovic as his former student Phillips when they were actually interested in what we call now today smart grid. This was in the mid-80s, and the idea was how you can optimally distribute the powers in the, say, US network. But then the research stopped because the Reagan government didn't want to fund activities in that direction. Now the situation is different because Obama is funding activities into that direction. However, the ideas that Kokotovic and his former student developed should be suitably adjusted to the website because there are some assumptions which are not reasonable. So that's what we did. There are also other people who use similar ideas for completely different problems. Aggregation into biological systems. I'm thinking in particular about the work of Mustafa Kamash from ETH, who use ideas, again, motivated by Kokotovic in this. I'm going to stop here. I'm just saying that Hideaki Ishii is going to give a plenary lecture at the MTNS in Groningen in a few weeks, and this will be focused on PageRank and in particular on aggregation. This is discussed also quite in detail into the Control System magazine page. Okay, just here, just a comment. Well, is PageRank the good indicator? And here is just a comment of PageRank and Twitter. So if you look at the White House, and if you look at White House government, the PageRank is 10 out of 10. On the other hand, the number of Twitter followers in the order of, say, 5 million. Well, if you look at Lady Gaga, then you get 6 out of 10. So from the PageRank viewpoint, is less important than the White House, but the number of followers is one order of magnitude different. So I leave up to you to decide which is the best way to rank it. Some references. Again, let me emphasize this paper if you want to get more interested in PageRank problem, multi-agent consensus, web aggregation. It's a long paper, took a long time to us to write it in the way that we wanted. We also, there is also a section which deals with eigenfactor and ranking tools. Other papers, I mean, this is the first paper that came out in transactions. The second one deals with web aggregation, and this one deals with loss communication links. There are papers by other people, including Boris, randomized algorithm to determine the eigenvector stochastic metrics, automation and remote control. This is the paper by Han-Fu Chen and colleagues from Chinese Academy of Sciences. There is an interesting paper also by Fer-Koch related to Markov chains and ergodic control and PageRank. I was actually in the PhD committee of Fer-Koch. It was actually a very interesting thesis, I think. In terms of eigenfactor references, these are a couple of, this is the thesis basically by West, and then there are a couple of papers by Bernstein on this. I think I want to make just a couple of quick conclusions, and I want to go back to some comments that Boris was making 2 nights ago when we had this panel discussion. So the conclusions are not directly related to what I was talking here, but Boris mentioned that when we first met, we were more heavily involved into robustness, and we have lots of interesting problems in robustness, which problems we can solve, which problems we cannot solve. That was a very inspiring, exciting period, as it is today, in a different fashion. So just some comments related to robustness. So here, Pavel knows the answer, so you should be silent. So let me read this. We use equalizing structures to compensate for the variation in the phase and attenuation characteristics of transmission lines and other pieces of apparatus is well known in the communication narrative. This is also related to some comments I was making the other night on control, communication, information field. The characteristics demanded of the equalizer cannot be prescribed in advance, either because are not known with sufficient precision or because they vary with time. Transmission lines, the exact length of which are unknown, or the characteristics of which may be affected by changes in temperature and humidity. And since the daily cycle temperature changes may be large. So there is uncertainty. So who wrote this sentence and when? Any guess? Don't be afraid. Want me to give the answer? Bodhi. 1938, variable equalizers, and Bodhi fully recognized the importance to control systems subject to uncertainty, what later on we called robustness. So just a little advertisement, Automatica this year is celebrating the 50th anniversary, and the editor-in-chief, Tamer Bashar, decided to have, so all Automatica papers are now freely accessible on the web until the end of the IFAC World Congress. So you can download any paper you want freely until then, in order to celebrate this anniversary. So Bashar had the idea to publish a number of survey papers on different topics, say ranging from systems, robustness, and so on. And Ian Peters and myself, we were invited to write one on robust control, and we had some concerns how to write it, something which was also inspiring for the future and so on. So anyway, we wrote it and it came out recently in May. And in particular, 70% of the paper is on classical results, and 30% of the paper is on recent developments. In particular, these recent developments, we discussed relaxations, approaches, SOS, so deterministic relaxations and so on, and also randomized methods. And we circulated around and got lots of constructive comments in addition to those reviewers. And we thank again Pavel for the great comments he made. So in case you are interested in robustness, but even if you are not interested in robustness, I would suggest to read maybe the introduction and the conclusions of this. On what is robustness today? What is the future of robustness? What are the successes of robustness? In terms of successes of robustness, there are many successes in robustness, but I want to mention in particular one related to robust economics. There is a book titled Robustness by Lance-Peter Hansen and Thomas Sargent. And what is remarkable, if you look at the book, it's robustness in the sense that we have in mind. If you look at the book, in my opinion, it is clear that Hansen and Sargent were inspired by our community, in particular thinking about two individuals, John Doyle, from the point of view of uncertainty, robustness, and so on, and Tamer Bashar on the game theory. In fact, I attended a talk that Sargent gave a couple of years back somewhere in the US, and it was really an H-infinity talk, a talk that we can give. So anyway, what is remarkable is that our community has been very influential, but nevertheless, I mean, this has been also very successful because Sargent received the Nobel Prize in Economics together with Sims in 2011. What is actually even more remarkable, Hansen also received the Nobel Prize in Economics last year. So both authors of this book in robustness received the Nobel Prize. So I think it's a major success. I want to conclude with a positive message. It's a major success for our community to be influential to people in economics so that they won't get Nobel Prize. So thanks for the attention.
May I start just a few words about robustness? Yeah, because just recently at a conference in Moscow, we discussed the issue of robustness, and my memory is about this word, robustness. So, and how is it in Russian? So we had some problem. Actually, robustness, as far as I know, it was first, this word was made in statistics. It was made by Box in 1950. Some robust statistics. Okay, and later it became more and more popular. And I remember that in 1980, Tsitkin and myself decided to write some paper about robustness in statistical, in statistics, again, statistical estimation. And we discussed the problem, how it will be in Russian. The first word which came to our mind was грубость, but грубость has some negative sense, and also it was used for some other, it has been exploited. Then stability, but stability, устойчивость, it is not the same as robustness. So there were several versions, and we tried to invent some Russian word, and finally we decided that robustness in Russian is the best word. So now it is more or less, very popular in Russian as robustness. But actually, if somebody of you can propose any word of this sort, it will. Actually, word крепкий очень хорошее слово. So, well, there are some ideas, and you still can propose it. Okay, sorry for intervention. Okay, and now questions. Please, questions to Roberto.
Just a quick comment. It's unfortunate that there is no Nobel Prize for engineering. So that other people get it.
There are several awards, but yeah.
At the beginning, you mentioned about ranking of sport players.
Yes.
Do you have some slides on that?
No, I don't have slides, but I forgot the name of the person, but in this article, at the beginning, we have some introductions and so on. We forgot the name of that person. We have at least one reference, or someone wrote a paper. No, I don't have a slide. But the paper, I was looking at the paper on this, say, Jimmy Connors, who is the best tennis player according to this ranking. There is a paper of it, which is an interesting paper.
And they have ELO coefficients in chess.
Excuse me?
They have ELO coefficients in chess.
Oh, okay.
Yes, they have some special system.
A special system, right.
Of ranking.
On the other hand, there is one comment that I want to make. What they claim at Google, now they have 200 indicators to do the ranking. And the PageRank is only one of them. I mean, it's a beautiful problem, not necessarily related to website. I mean, we have seen that for ranking journals, it's very successful. So it's one of these indicators. At the beginning was the main one, now it's one of many. Because also, I'm not an expert, but the direction where web searching is going, for example, is related to semantics. If you are typing Moscow hotel, are you looking for a hotel in Moscow, or for looking hotel with the name Moscow somewhere else in the world? And this clearly has nothing to do with PageRank. So it's still a paradigmatic problem, which I think is quite interesting for many different ramifications. Also, I would like to emphasize, I mentioned that briefly, but let me emphasize again, the educational aspect. If you want to teach students, undergraduate students, for example, Baron Frobenius theorem, I think it's an interesting way to present it, that it's perhaps fashionable and you can get different interpretations and so on, and you can get students maybe excited about that.
Yeah. And about PageRank and how is it used now. Yesterday we met with some people from Yandex and they directly said that they don't use PageRank now. Some ideas of they are exploited, but not PageRank in its initial form. So, because as you said, there are many factors which they want to exploit. Okay, other questions?
About the rate of conversions of Las Vegas method you described in the middle of the talk, I guess that the Markov chain Monte Carlo, simple algorithm Markov chain Monte Carlo, it seems better. That is, it is not obvious that Las Vegas works better than Markov chain Monte Carlo. I don't know the precise answer, but it seems probably likely that Las Vegas is worse. What do you think about this?
I don't have an answer. We use the Markov chain Monte Carlo in other problems totally unrelated to this. For example, we have a paper, Mario Sneyer, Fabrizio Dabene and myself, which is coming out, I don't know, the next couple of months in transactions automatic control. This is a paper which deals with system identification. So it's a mixed model, which is in between, say, the classical stochastic model, where the noise is stochastic, and when the noise is purely deterministic. So it's a mixed model. So in that case, we provided, at least for me, interesting general framework, but then we also have an algorithm. And the specific algorithm we have is a Markov chain Monte Carlo. However, we did not analyze yet, the conversion state. So I think if you're interested in, you can find the preliminary version of that paper in my website. By the way, I didn't mention, in case you're interested in some material, go to my website so that I can get a better PageRank. And you can download papers, slides, reports.
Thank you.
Please, questions? Okay, Roberto, thank you.